Hello friends, welcome to my YouTube channel Obsession for Learning. Here I teach you step by step about design of structure manually and by using software. Okay, without doing delay, let's move to our topic. Today's our topic is about design of slab. Okay, actually we have already done half part of design of slab. Now we're gonna continue from the step number 5. You can see here in the step number 5 we have your area of steels along longer spans. We have already done in our previous video for calculating the reinforcements along short spans, okay, which is represented by Alex. Yeah, here you can see in step number 5 here we have area of steel along longer span, which is represented by Ly. Okay, for under reinforced sections we have one formula as per IS 456 2000. Mu is equal to 0.87 FYAST YD primes times 1 minus FYAST by FCK BD. Okay, it is in Annex G as per IS 456 2000. Okay, here only one thing we have to do. Rest of the things are quite similar to which we have already done in our previous video for calculating the area along such spans. The only one thing is difference, that nothing but calculating the effective depth. Yeah, for calculating the effective depth, what we actually have to do is we have to subtract half of main bar, first main bar, similarly half of second main bar, okay, from the defective, it means effective depth of slab. Now by substituting the value of d primes on this formula and rest of the value as well, such as Fy, Asty, we are getting here, we have got here 18.23 mm squares, which is less than minimum area of steel required, which is equal to 0.12 percentage of B into overall depth D. Okay, you can see over here we have required ASTY, which is 150 mm square. It is 0.12 percentage of B into D. Okay, after calculating that value 0.12 percentage of B and D, we getting 150 mm squares. Okay, that's why I'm taking this ones. I have already calculated in the previous video. You can check my last video as well. Okay, and you're gonna see 150 mm squares, which is the minimum still required for slab. Now you can see here I'm assuming 10 mm bar, right? Okay, area for individual bar, which is pi d square by 4. We already know about this formula, right? So by calculating that, we have got a 78.54 mm squares, and you can see here the spacing is equal to the area of individual bar divided by area required into 1000 mm, or we can say per meters. Okay, in mm we're gonna keep here thousands. So simply calculating these terms, we are getting here 523.6 mm, which is, you can clearly see here, which is greater than 300 mm. So minimum spacing you can provide the 300 mm, or for more economical we can also provide less than 300 mm. Now I have provided here 200 mm. Okay, you can clearly see here. Okay, and after that we have to calculate the provided area just by replacing the value, spacing and area. This one is area. Now I have to calculate the area. It means I have to divide these terms by spacing, so I'm gonna get the provided area. Okay, that's what I'm doing here. You can see these upward terms are same, and this one is nothing but it is the spacing. I have divided these terms by spacing, then I'm gonna get here area provided, so which is greater than AST required, at the same time minimum area still. In this case area AST required and minimum area of steels are same. Okay, now we can say that it is safe because provided area is greater than minimum area of steels. Okay, in step number 6 we have to check for shear at shorter spans, and at the same time we have to check shear at longer spans also. Okay, at first what you have to do is we have to calculate the shear force, which is represented by V. You can see here, right? And we have formula for shear force, WF Lx by 2. Wf is nothing but it is the factor load. Lx is length, or you can say that, yeah, simply length in shorter spans, right, divided by 2. We're gonna get the shear force at one side. Okay, so by substituting the value of Wf and Lx in this formula, then we have got here by calculating these ones 12.87 kilonewtons, right? Similarly, now you can see over here, so what you have to calculate is nominal shear stress, which is represented by tau v, and we have formula v by bd. Okay, by substituting the value of v by bd in this formula, okay, and by calculating we have got here, you can see here 0.123 Newton per mm square. Okay, because this one is stress. Okay, now here we're going to calculate the percentage of steels for tension, PST. You can see here as a formula we have here, it's 100 AST by BD. Okay, this is the AST provided. Okay, this is 100 divided by BD, 100% actually. Okay, and by putting the value of AST, B and D on this formula, we have got here 0.499, and I have just round of it, and I have taken 0.5 percentage. Okay, so for percentage of steels 0.5, look at here for tension zones. Okay, from table number 19, from table number 19 we can calculate the design shear strength of concrete, which is represented by tau v. Okay, so for 0.5 percentage and M25, from table number 19 we have got 0.75 Newton per mm square. Okay, now what I have to calculate is, I have to calculate tau c prime, which is nothing but it is a k times tau c. Okay, tau c is here, and k, what is the k? K is nothing but it depends on the overall depth. Now we have overall depth is 125 mm, so k we can take it as 1.3 as per IS 456 2000 class 40.2.1.1. you can see here. Okay, by replacing, or sorry, by substituting the value in k and tau c. Okay, look at here, I have substituted. So by calculating these ones, we have got here 0.975 Newton per mm square, which is greater than tau b. Tau b, you can see here 0.123. It is nominal shear stress. Okay, so you can see here is tau c prime is equal to 0.975, which is greater ones than tau v. This is required, this is provided. I mean to say that which is in the slab, this is the strength which is in the slab, and you can clearly distinguish by comparing these two, stress and strength. Strength is greater, so it is safe. Okay, now here both along shorter spans and longer spans, here is okay. You can see here strength, this is strength. Strength also, it is internal stress which act for resisting the stress. Okay, this nominal stress, we have to resist that nominal stress. So strength we have more, so if we have more strength, so we can easily resist. Now in step number 7, we have to check for deflection for shorter span, so which is represented by Lx. You can see here from the deflection criteria, we have one relations, L by D, which is less than or equal to alpha beta gamma delta H, right? And okay, here you can see the ratio of length to the depth. Okay, and which must be larger or equal to this multiplication of modification factors. Okay, now what we actually have to do is we're going to multiply these all modification factors, and you can see here we have only 26. We have to multiply 126 into 2 because rest of the terms we have only 1. So when we multiply 1 with any other terms, so it becomes that terms, right? So we have 26, we have to multiply here 26 and 2, so it comes as 52 if I'm not wrong. So if we divide these terms, and we're gonna get less than 52, so it is clearly showing that, and we can say that the relation is satisfied. So um, hence both along x and y directions of slabs are safe in deflection respectively, right? Yeah. In step number 8 we have to check for development length. Here also we have one relation. You can see over here is LD, which is less than or equal to 1 by 3 times M1 divided by V plus L naught. Okay, where we can say LD as it is development length, M1 moments, and B shear force, L naught anchorage length. Okay, and you can see here for MI, it is like quite similar to calculate the moments. Like this is formula we have taken from NXGI Expo 6 2000s. Okay, so we have got here, you can see 21.53 by calculating this value, right? So shear force 12.87, this shear force we have taken from the previous calculations where we have checked the shear force. Okay, from there I have taken this 12.87. L naught is 0 for straight bars, or like in some other case we can also consider sometimes 12.5 or D. Now LD is development length. We have for one formula, this is sigma s into 5 by 4 tau bd. Tau bd is nothing but it is a design bone stress, and sigma s is equal to nothing but it is 0.87 Fy. Okay, as per clause 26 2.1. By putting the value or by substituting Fy tau bd or 5, then we're gonna get here, look at here, tau bd is equal to 1.4 Newton per mm square for M25. And one important thing what we have to do is for different bar we have to increase it by 60%. Here you can see tau bd is nothing but 1.4 into 1.6. We have increased that 1.4 in by 60%, so we have got here 2.24 Newton per mm square. So by calculating or by substituting the value on this formula, look at here, again this one, so we're gonna get this one. So by calculating these terms we have got here 485.49 mm square. Similarly, by putting the values in this formula also we have got here 2174.75 mm. This is clearly greater than 400 and something value, so it is satisfied. So it is safe in development length for both directions along x and y respectively. Yeah, this much for design of slabs. This is complete video of design of slab. So thank you so much for watching this video, and if you guys really like my video, or if you guys really feeling like that or really getting help from this video, please don't forget to give thumbs up, subscribe my channel, hit the bell icon for getting more notification. At the same time, if you guys have any confusion, please leave the comment in the comment sections. I will make video based on your comments.